Imagine a vast cloud of gas and dust, a nebula stretching light years across the cosmos. This was the solar nebula, the birthplace of our Sun and its planetary family. About 4.6 billion years ago, this nebula began to collapse under its own gravity. Perhaps a nearby supernova explosion triggered the collapse, sending shockwaves through the nebula. The nebula began to spin faster as it contracted, much like a figure skater pulling in their arms. As the nebula spun, it flattened into a rotating disk with most of the mass concentrated at the center. The temperature at the center increased dramatically due to the gravitational compression. This central region, the protostar, became the precursor to our Sun. The surrounding disk, a swirling mix of gas and dust, became the raw material for the planets. Tiny dust grains began to stick together, forming larger clumps. These clumps continued to grow, attracting more and more material. The solar nebula was a chaotic environment, with collisions and gravitational interactions shaping the early solar system. Different elements and compounds began to condense at different distances from the protostar. Closer to the protostar, where temperatures were higher, only heavier elements and compounds could condense. Further out, lighter elements like hydrogen and helium remained gaseous. This temperature gradient played a crucial role in the composition of the planets. The inner rocky planets formed from heavier elements, while the outer gas giants formed from lighter elements. The scene was set for the formation of our solar system. The solar nebula, once a vast cloud of gas and dust, was transforming into a structured system of planets orbiting a central star. As planetesimals continued to accrete, they grew into larger bodies called protoplanets. These were the embryonic stages of planets, still undergoing significant changes. Protoplanets possessed stronger gravity than planetesimals, allowing them to attract even more material. They cleared out the surrounding space, sweeping up remaining planetesimals and dust. The process of accretion was not yet complete, and protoplanets continued to collide and merge. These collisions were often violent, releasing tremendous amounts of energy and reshaping the protoplanets. The early solar system was a dynamic environment, with protoplanets jostling for position and competing for resources. Gravitational interactions between protoplanets influenced their orbits, sometimes leading to close encounters or even collisions. The composition of protoplanets reflected the materials from which they formed. Those closer to the protostar were primarily composed of rock and metal, while those further out contained significant amounts of ice and gas. As protoplanets grew larger, their interiors began to differentiate. Heavier elements like iron and nickel sank towards the center, forming a core. Lighter elements like silicon and oxygen remained closer to the surface, forming a mantle and crust. This differentiation process released heat, further heating the protoplanets. The heat generated by accretion and differentiation caused the protoplanets to become partially molten. Volcanism was widespread, releasing gases and further shaping the surfaces of the protoplanets. The early solar system was a hotbed of activity, with protoplanets undergoing constant change as they evolved into fully formed planets. The stage was set for the emergence of Earth, a rocky protoplanet destined to become a haven for life. Section 4. Earth's formation, a violent beginning. In the region where Earth would eventually form, a protoplanet began to emerge from the chaos of the early solar system. This protoplanet, initially a collection of planetesimals, grew larger through relentless accretion. Collisions with other planetesimals and protoplanets were frequent, releasing vast amounts of energy and reshaping the young Earth. The early Earth was a molten world, its surface a fiery landscape of lava flows and volcanic eruptions. The bombardment of planetesimals continued, delivering more material and further heating the planet. As Earth grew larger, its gravitational pull increased, attracting even more debris. The process of differentiation began, with heavier elements sinking towards the center to form a dense iron-nickel core. Lighter elements rose to the surface, forming a mantle and a thin rocky crust. The early Earth was a hostile environment with a toxic atmosphere and no liquid water. The intense heat from accretion and differentiation prevented the formation of oceans. Volcanic activity was rampant, releasing gases into the atmosphere and contributing to its composition. The early atmosphere was primarily composed of hydrogen and helium, captured from the solar nebula. However, these light gases were eventually lost to space due to Earth's relatively weak gravity. A secondary atmosphere began to form, composed of gases released from volcanic outgassing. This secondary atmosphere contained water vapor, carbon dioxide, nitrogen, and other volatile compounds. As Earth cooled, the water vapor began to condense, forming the first oceans. The early oceans were acidic and hot, but they provided the environment for the emergence of life. The stage was set for the next dramatic chapter in Earth's history, the giant impact that would lead to the formation of the Moon. Section 5. The Giant Impact Hypothesis, Birth of the Moon. The prevailing theory for the Moon's formation is the Giant Impact Hypothesis. This hypothesis proposes that a Mars-sized object named Theia collided with the early Earth about 4.5 billion years ago. This collision was a cataclysmic event, releasing an unimaginable amount of energy. The impact liquefied both Earth and Theia, vaporizing vast amounts of rock and sending debris hurtling into space. The impact was not a head-on collision, but rather a glancing blow. This oblique impact imparted angular momentum to the Earth-Moon system, explaining the Moon's current orbit. The debris from the impact formed a ring around the Earth, similar to the rings of Saturn. This ring of debris gradually coalesced under its own gravity, forming the Moon. The Giant Impact Hypothesis explains many of the Moon's characteristics, including its composition and its orbit. The Moon's composition is similar to Earth's mantle, supporting the idea that it formed from material ejected from Earth's outer layers. The Moon's orbit is tilted relative to Earth's equator, further evidence of the oblique impact. The giant impact also explains Earth's tilted axis, which is responsible for our seasons. The impact is a defining moment in Earth's history, shaping its future and laying the foundation for the development of life. The Moon's formation stabilized Earth's rotation, preventing extreme climate fluctuations that could have hindered the emergence of life. The Moon's gravitational pull also creates tides, which have played a significant role in the evolution of life on Earth. The giant impact was a destructive event, but it also had creative consequences, giving rise to our celestial companion and shaping the destiny of our planet. Section 6. Lunar formation from debris to celestial orb. Following the giant impact, a ring of debris encircling Earth began to coalesce under its own gravity. This debris, a mixture of vaporized rock and molten material from both Earth and Theia, gradually clumped together, forming larger and larger bodies. The process of accretion continued in the debris ring, mirroring the earlier stages of planet formation. Smaller clumps collided and merged, building up the mass of the nascent Moon. The early Moon was a molten world, its surface a sea of magma. As the Moon cooled, a crust began to form, solidifying the surface. The intense heat from the impact and subsequent accretion caused the Moon's interior to differentiate, forming a small iron core and a mantle. The lunar surface was bombarded by meteoroids and asteroids, creating the craters that we see today. The early moon was volcanically active, with lava flows resurfacing parts of the lunar landscape. The moon's gravitational pull, though weaker than Earth's, played a role in shaping its internal structure and surface features. The moon's lack of atmosphere and its relatively small size meant that it cooled much faster than Earth. This rapid cooling led to the cessation of volcanic activity and the preservation of the ancient lunar surface. The moon's formation was a relatively rapid process occurring within a few million years of the giant impact. The moon's final form, a solid, rocky sphere orbiting Earth, was a testament to the powerful forces at play in the early solar system. The moon's presence has had a profound influence on Earth's history, shaping its rotation, tides, and even the development of life.